All right. Let's see if we can fix that. I'm going to show you guys my screen so that people at home can see this. And maybe if I pin it, you guys in the room will see this as well. Wait, can you hear me, Andrew?
He looks like he's talking.
It does look like he's talking. Hold on, let me.
Or eating. Conrad say something to make sure Andrew's not.
No, sometimes this is weird. Oh, that's volume here.
Why is he wearing?
Andrew, I can't hear you. Can Uditi or Conrad?
How
Can you?
about now?
Now we can hear you.
All right, my mic was upside.
Okay.
Yeah. All right.
Show you guys the setup that I've built. All right. So here we have a battery. I also increased the voltage of the battery by putting 2 AA's, and it's also just a little easier for me to work with because they have leads built to this little holder. Okay. That comes out, goes into this multimeter, then out of the multimeter into the breadboard. And I actually use the power rail of the breadboard. And that means that every resistor that goes from power to ground is parallel, because this whole left side, you guys can't see. So the whole left side, that's like that red line, is all hooked up to one another. And the whole other side, this blue line, you can kind of hardly see it here, is all hooked up to each other. So we've come in from the multimeter, this black wire. We've gone down the one side, through every one of these resistors into the other side, which is then back to ground and back to the batteries. So that's just 23 resistors in parallel. Okay, set up with a battery pack and a multimeter, all in series. These two are in series with one another. Yes.
That low resistor on the other side.
No, nothing right now. So then on the far end of all those, I have another multimeter. So this one is set up across from positive to negative side. So hopefully you guys can kind of guess if I draw a picture of what we're doing here. I promise this is the last day we're doing this. We're going to move into magnets tomorrow. But I just felt like I needed to really like get some closure.
Like my cocoa implants.
What's that, Andrew?
Like my cocoa implants.
Yeah.
Magnets.
Yeah, exactly. You still need to give me a diagram of those so we could talk about them and see how they work.
You gotta eat them. Yeah.
All right, so I know it was a little messy with wires and stuff, so I just want you guys to have a clear idea of what this is actually looking like. What we have is a battery. Now that's, in this case, 2 batteries in a battery pack, but you could think of them as just 2 batteries in series, whatever. I'm going to kind of treat them as an EMF with an internal resistance. And then we have resistors, all parallel, continue, 23 of them until the last one. And then out here, we have another meter. I left out one of my meters. Here, we also have a meter.
Mr. Barney,
Yes.
why did you do 23 specifically?
Because that's how many holes there were on the, yeah, that's what fit.
Okay.
I would actually have done more, and if we need to, we always can, but I think this is where I'm stopping.
And they're all
But
equal resistance?
They're all equal resistance,
Okay.
and that's to simplify things as well. So those 23 resistors, if I want the equivalent resistance, I end up with 23 times a single resistor. I mean, well, divided by a single resistor. So our total resistance is 1/23 of a single resistor. And this guy is a 220 ohm resistor. I use the smallest resistor because I'm trying to get smaller and smaller resistance.
Wait,
Yes.
220, like, that's small?
Yeah, I think that's the smallest one we have.
Oh, that's crazy. Because like when we do like the equation, we have like 3 or 5 or.
Sometimes, but sometimes it's kilo ohms, right? And so if you look in the back, like we have a whole rack of a whole bunch of different resistors, and that's the smallest one we had in the room. Okay. So now, just based on the placement of my multimeters, these multimeters, they're multimeters because they can do multiple measurements. They could be voltmeters or ammeters. They can even measure resistance. So we'll do that at the very end and see how our internal resistance comes out. Which should be a voltmeter and which should be an ammeter in this picture?
First one is a volt.
So first, top or bottom?
Top left.
That's a voltmeter?
I would say no.
Isn't that an ammeter, the top one?
Is an ammeter. Is an ammeter. Can you tell us why?
Because it's supposed to be in series, because the current has to go through the ammeter to measure it.
Yes, current has to go through the ammeter to measure it, as opposed to a voltmeter is comparing this portion of the circuit to this portion of the circuit. So when we measure voltages, we're measuring potential difference, the difference between this point and that point. So the voltmeter actually should be kind of outside of the circuit looking in. And the ammeter has to be in the path of the current. So far, so good. So we're going to collect these two readings, and we're going to do it, and then I'm going to remove one resistor. Then I'll tell you the number again, and then we'll remove another resistor. And we'll collect that number over and over again. Do you see the list there? The spreadsheet? Did you open the spreadsheet? It's for today's class assignment if you open a spreadsheet. Sorry, Daniel, I already made it just to. It is on Google Classroom. Sorry, I didn't tell you that. Okay. Any questions or comments or thoughts on this so far? So why are we trying to put so many resistors in to get a really small resistance? Because I know there should be some little R in here. And if these external resistors have a small enough R, then there will be a measurable voltage drop across the internal resistance. Or at least that's what we're hoping for. Yeah? All right. Yes, sir. I'll do it right now. So let me stop my screen share.
No, not Andrew. And that's outside.
Try and refresh that and see if you can see it.
Okay.
You're in? Okay. So right now we're going to type in this first row. I'm going to hook everything up and let's see what we get. All right, powering on. My voltmeter currently is saying 0 volts. That's good. Okay. My ammeter is reading 0 amps. So for those of you at home, voltmeter, actually I can put these probably next to each other, make life a little bit easier for everybody. Maybe. As long as I don't cross any wires. Can you guys read these? Kind of read them?
Yeah.
Yeah? Cool. All right. So everything looks this, put this over here. All right, let's see how we do. I'm going to close the circuit. Circuit is now closed. And I have 0.28 amps and 2.71 volts. Okay. Take one resistor out. Next row. .26 and 2.62 volts. Take one resistor out.
Do you have to open it every time you take them out? Is that like a safety thing?
Probably not. I probably don't have to. I'm not worried about like me touching and getting a shock. I'm trying my best to keep this closed as short as possible so that I'm not draining energy from the the voltage. If you think I could like pull them and you'd get those written down really fast, then maybe I could do that. But I think this is just,
Yeah, I was just wondering.
yeah. All right. 0.26 and 2.72. Okay. 0.2454 and 2.70. 0.24 and 2.79. 0.23 and 2.80. 0.22 and 2.82. I'm going to go fast now. 0.205 and 2.82. 0.19 and 2.84. 0.18 and 2.82. 0.17 and 2.86. 0.16 and 2.87. 0.15 and 2.88. 0.13 and 2.89. 0.12 and 2.90. 0.11 and 2.92. 0.1 and 2.93. 0.08 and 2.94. 0.07 and 2.96. Does it just seem like one every single time? 0.05 and 2.97. 0.04 and 2.99. 0.03 and 30. 0.0, we'll call it 2, and 3.01. Now, I think I should probably, while I have this set up before I change anything, instead of just 20 ohms, should I go a couple higher ones as well? I'll just put them in individually because I don't have anything above 220. So let's put a couple of those in here.
Mr. Varney,
He just left the room.
Okay, Andrew.
Hi, Andrew.
yeah, I'm just thinking whoever's like, Daniel, you're on the spreadsheet, you should make a column for like the resistance based on the measured current and measured voltage, like column B divided by column A. And like carry it down just to see how it compares.
What's that?
For the R,
There should be like a column on the spreadsheet that takes like the measured voltage and divides it by the measured current, so you can compare the measured resistance to the actual resistance.
Yes, go ahead and do that. You want to do that, Daniel? Okay. And I'm going to explain, actually, this is something, I have a little comment in the top of the total resistance. The measured resistance is going to be much more accurate because these resistors have plus minus 5% error. And so that's kind of an issue because, well, 5% sounds small, right? But then 5% multiplied out by 23 resistors. If each one of them was 5% on the high side, we could get a way big error on the far end, right? That propagation of error gets really big. In reality, most likely some will be above and below and above and below, and they'll cancel each other out. So I don't think it's terrible, but it's good to calculate, actually. So thank you, Andrew. That's a good point. So I don't want to do too many of them. Just want to be quick about this, honestly. So we'll start with 1,000. So do you know how to like have that formula go all the way down the column? There you go.
I
Cool.
just did it.
Thank you. All right, so 1,000 ohm resistor. Let's add this.
It's
And
just one, right?
what?
It's just one resistance.
It's just a single, yeah. I'm just gonna do like a few of them like that I just have on hand. And this is, we can't get a reading on our current. So I'm actually going to switch this to milliamps. I should get .7 and 3.03. But that's,
0.7 million.
yeah.
you want my zero?
Hmm?
It's 0.7 million.
Right.
Oh,
Points.
0.7 million.
Yeah. So I think that seems right. Let's go a little closer because I don't want to. I feel like that seems way off from.
The measured resistance and total resistance are a lot different for that one.
Okay. Let's try another one. This should be 330 ohms. So it's possible that this we're reading this 0.7 milliamps wrong. I'll tell you guys in a second. Hold on. Let's do, this one is 330 ohms. Comes out to 9.4 and 2.99 volts. Give me a measured resistance on that.
Much closer.
Okay. Let me double check the. Yes, sir. 1,000% what?
Error.
Yeah, it's off.
You sure it's a 1K ohm resistor? Like
Well,
maybe
that's why I
got
was
mixed up.
double checking, so I'm pretty sure. I'll try it again. Brown, black, red. Brown, black, red, gold is what I had. Yeah, this came out different. So this is it for 1,000. 3.1
So this is, Daniel, this is the 1000 ohm. Yeah, that row, 1000 ohm resistor. 3.2,
Wait,
3.1, and then 3.02. Better, right?
Yeah.
Let's get
should
rid
I delete this row?
delete that row. Okay. So let's go unscientific to just delete data that doesn't match our results, but I'm pretty sure I just grabbed the wrong resistor. All right, so where are we? Let's go like pretty high. Now that we're getting things that seem to match. Hey, and what's the percent error? Is it 5%?
Let me make a formula for that.
All right, here we have, this is, according to the box, 6,800 ohms. Ready? And we're in. And we've got 0.5 milliamps, and we've got 3.04 volts. Okay. Try another one. We might be getting to the, let's go 15K. And then we'll do 20K and we'll be done. So this looks like we might have to, oh, I didn't close it. 0.3 and 3.04. Okay. So we're getting pretty off on these last ones, huh? 50%. What do we say that was 1,500?
Oh, the last one.
20K. Somebody who has their iPad open, can you just Google brown, green, orange, gold resistance? And we'll do the last one.
$15K.
Okay, so something odd is happening. Let's do this last one. This is supposed to be 20K. All right. And we'll close it. We're also seeing a pretty high variability on the readings.
Yeah, why is it like?
I don't know. I don't know. That's not a great sign for like being happy with our data. So the fact that it's going from 0.2 to 0.3 to 0.4, 0.1 to 0.5 for our current, like, I don't even know how to give it a number. I'm going to change it to, so 0.1, I'm going to go 0.16 milliamps, 0.16 milliamps. And that's 3.04 volts again. That's better. Let's try the 15. All right. Try for 0.21 milliamps and 3.04. Yeah, there we go. Cool. I'm happy with those numbers. Let's get rid of that 48% error one. All right, so we got some data. Now, what can we do with this data? First off, I want to graph it.
I mean, you did that one that was 46%.
Yeah, we got rid of it.
There's another one.
You still have one with 46% error. Can you do the 220 ohm one again?
Ooh,
Yeah, I won't-
This row?
sure, sure. Glad I didn't just rip this all apart. 220 again by itself. And it's okay to have one that's way off. It's one data point. That's part of the reason why we collected all this data. So how about 2.86 for voltage and 13.33 milliamps. .33 milliamps.
So much better.
Cool.
Should I delete the other 220?
Delete the other one. Okay. So what do we see when this 3.04, 3.04, 3.04 happening over and over again? What do you think's going on there?
You've reached your terminal voltage, maybe?
Yeah, probably we're getting close to the terminal voltage because when we end up putting a really big resistor outside the battery, the voltage drop that's in the battery is almost non-existent. Right? Does that make sense? So probably we're thinking terminal voltage is probably about 3.04. Let's take a look at this on a graph. I love graphs, so. Let's insert chart. We're going to switch this to a scatter plot. We're going to series. Can anybody think, is it better for voltage or current to be on the X or Y?
Voltage on the Y.
That's kind of what I wanted to do. So we'll remove this here. And our Y axis.
Is there a reason why you put voltage on the wall?
Not necessarily. It could go either way. I feel like by changing the resistance, in my mind, when I change the resistance, I'm changing the current, and that will give me a different voltage drop. But yeah.
Would that be a linear
It's looking linear.
graph?
With that little weird thing in the bottom right.
Yeah. So I'm sorry, I'm floundering here with my series. I think I should be able to add, we got a problem that all our spaces are perfectly spaced. That's why it looks linear too. What I really need to do is, series, it's gotta be in here.
Has to be over I.
Hmm?
It has to be linear, right? Because V over I.
No, because R is not constant, Andrew.
Oh, right.
So this is technically, it'd be almost better to have this as a 3-dimensional graph with V, I, and R. And then depending on which way you're moving, like in the I and R, you get a different voltage output as like a height of like this plane. We're not going to go that far. We're not going to get crazy.
Let's just make a few. Why don't we just make a few graphs with like VI, VR, and IR or something like that?
We could use column B
So I just have a problem right now with my graph. I'm sorry, guys. I need the y-axis to be and the x-axis to be current, and it's not current right now. Yes, that's what I need to do. And actually, thank you. X-axis should be current, and y-axis should be voltage. Here we go. Now let's change our max and mins here. Now factor, default, minimum. What's our smallest? Should I do 2.5? Does that work? Yep, and that's what we got here. So if we assume that 3.04 is our terminal voltage, then we can calculate for every one of these rows our voltage drop due to internal resistance, basically by subtracting 3.04 to one of these numbers. Is that making sense?
Wait, subtracting 3.04 to what?
I'm gonna do it over here. The actual voltage that we measured,
Oh, okay, yeah.
right? So our measured voltage drop. What is this terminal voltage? Did somebody type that in?
I think it was on here.
This 2.81 too?
Yeah, I think it was on here when you started.
So terminal voltage, that's what we measured. I'm not gonna call this terminal voltage. Let's change this to internal voltage drop. And that's gonna be equal to 3.04, if we're assuming that that's right, minus the measured voltage. And that's how much was dropped. And then we should be able to reverse out an R because the voltage drop divided by the current should give us that R. Call it little r, or should I just call it internal resistance? It's going to equal drop divided by current. They're all very, very close to 1, except for some weird ones down here. That seems reasonable. 1 ohm resistance inside.
Can we measure to find out?
Oh, yeah. What did I tell you guys? Absolutely. Let's do that. So let's disconnect this. I'm plugged in. If it comes out to be like 300, I'm just going to start talking about magnets. That's all I'm going to do is just stop this. Stop putting you guys through this. All right. On. Should I show it to the camera? Stop sharing. Okay. Let's see. Turn it to ohms. It's not closed yet. Hello. All right. Ohms. And we're thinking, I'll put it on 200. That's the smallest. Look, it's like 2K. These are all ohms value readings on top here. So 200 ohms. Right now, it's basically no connection. Oh no, we're not getting anything. Huh?
Isn't that one?
No, it's not one. Because it's one here too. So we can double check here.
What kind of battery are you using, Mr. Ronnie?
Alkaline, double A's, 2 double A's. Oh, wait. I think I got it. So on these plugs, they tell you which reading, there we go, which reading each one of these things is for. So like I was in the milliamp plug. Over here, you could see ohms. So I got to switch that over to there. There's like, all right. So right now I have the 220 ohm resistance in there. I know it's a mirror image, but it's, let's see. Oh, please, please, please come out right. Put it on 200. No, I got nothing.
So magnets.
Mr. Varney, I looked it up and it says that like 2 AA batteries like in series would have an internal resistance between 0.2 and 1.8.
So Andrew confirmed with a Google search, and that's what we're going with. Thank you, Andrew. I still think our calculation was right, even though
I think it is if we're smack in the middle.
yeah, I'm really happy with that. All right. Thanks, guys. I'll see you tomorrow.